David Smith here with one more flipped classroom math lesson. 3 tips. First, you can adjust the playback speed faster or slower as you desire. Second, you can pause the video at any point to catch up with your notes or jot down some questions. Third, you can turn on the captions and read my words on the screen. Today's lesson covers this weird thing called antiderivatives. So let's review real quick this basic concept in mathematics called inverse operations. And these are operations that basically undo each other. And you already know about these, maybe if you don't even know them in this particular way. So I want to review that first, and then we'll take a look at what antiderivatives are. So first off, addition and subtraction are inverse operations. If you add 4 to any number, and then subtract 4, which is the inverse of adding 4, you're back at the same place. So that's what inverse operations do. If you do 1 and then you do the inverse, you wind up back where you started. So same thing with multiplication and division. If you multiply a number by 6 and then divide the result by 6, you're back where you started. Same thing with exponents and logs. If you raise something to a power and then you take the log with the right base of that result, you're going to get back to your original number. So now let's take a look at derivation. Now you might know derivation by this term derivative because we've been talking about taking derivatives. It is really the process of derivation, and it also has an inverse operation. There's a very specific name for that, but we'll get to that in the next lesson. This lesson just talks to you about undoing derivatives or derivation, hence antiderivatives. Now, I'm trying to map this lesson to most textbooks which tend to introduce this process by first talking about antiderivatives, but really what we're talking about is taking an integral, and this is calculus. So let's take a look at what that means, what antiderivatives are. Okay, let's take a look at a very simple expression, 2x squared, and let's talk about the process of taking that derivative so that then we can come up with a way to reliably get the antiderivative, which is just going backwards down the process. So check this out. You know already from this class that we can use the power rule on this expression to take the derivative. And so the derivative of this would just simply be 4x. Okay, so remember, we have this rule for that. It said 4 f of x equals ax to the n power, then f of prime of x is going to equal nax to the n minus 1. So basically, you just take the power, you multiply it by the coefficient of x, that's the na, and you reduce the power by 1. So now it's n minus 1. So pretty simple process. Now we can use this to map out a rule for taking the antiderivative for an expression like this. And basically what that means is, what do we do to this term to get back here? Now this is a big critical thinking step to do that, but I'm going to encourage you, pause the video right now and take a look at how might you articulate a rule like this one to go backwards along that process. And maybe take a minute and really think about that, work this example. What would you do to this term to make it go back to that? So give that a try and then come back. Okay, here's what I cooked up to explain the process and to show you the rule, which I've put right there. So watch this. So if f of x is ax to the n, then we know from our prior chapter that to get the derivative of this function, we just multiply the coefficient, like I just mentioned. We have nax, and we reduce the exponent by 1. That's the n minus 1. Now, if our f of x is in this form, ax to the n, but now instead of looking for the derivative of this, we're looking for the antiderivative. We need to go the other direction on the chain. The antiderivative is just a divided by n plus 1 times x to the n plus 1. Because remember, we subtracted 1 from here, so the resulting exponent was 1 less. So this is 1 less than the antiderivative's exponent. So that's going to be n plus 1. And then when we take the derivative, we're multiplying the exponent by the coefficient before we reduce it, because this is nax. So we have to increase this and divide, which is the opposite from multiplying. So we have a over n plus 1 times x to the n plus 1. And indeed, this is the reverse of the power rule for taking a derivative. This is the antiderivative using kind of the antiderivative power rule, if you want to call it that. Okay, let's do a couple problems just real quick to kind of burn this in a little bit. So I summarized our findings from the last two boards. If f of x is ax to the n, then f prime of x, the derivative of f of x, is just nax to the n minus 1. Okay, so that's our familiar go-to. If you're undoing that, you want to go backwards along the chain, and you're starting with ax to the n, then the antiderivative of that is a over n plus 1 times x to the n plus 1. Okay, summarizing, done. I want you to pause the video and try these two. Find the antiderivative of these two functions, write those down, and then come back. Okay, let's see how you did. So check this out. 6x is our function. The antiderivative, I broke it out, showed you all the steps according to our rule. It's coefficient over exponent plus 1. Remember, there is a 1 there. That's our exponent. So it's over 1 plus 1 times x to the 1 plus 1. So now we just simplify that down. That's 6 over 2 to the times x squared. And then 6 over 2 obviously is 3. So our antiderivative of 6x is 3x squared. Okay, let's try this other one. A little bit more complicated, but not by much. Here's our function, 2x to the third. The anti is going to be 2 over n plus 1. Our n is 3, so it's 2 over 3 plus 1 times x to the 3 plus 1. So that becomes 2 over 4 times x to the fourth, which is 1/2 x to the fourth. Now, you can check your work here simply by taking the derivative of these two expressions, and you should wind up back here. So go ahead, pause the video, and do that just to convince yourself that this process is right. Okay, let's see how you did. Using the power rule, I just multiply my coefficient by my exponent. 2 times 3 is 6. Reduce my exponent by 1, so that's x to the 1. So that's just x. So that gets us back to 6x, which is indeed what our function was in the beginning. Woohoo, success. Let's try the second one. I'm just going to multiply my power times my coefficient. 4 times 1/2 is 2, and I reduce my power by 1. So this becomes 2x to the third, and woohoo, we're there. Okay, let's do one more problem here before I get a little more complex with the antiderivative process, just to illustrate a point, okay? So go ahead, pause the video. I think you know enough using our rule here to find the antiderivative of this expression. So go ahead, pause the video, work that math, and come right back. Okay, so I broke it out just in a bunch of steps. My coefficient, my a, is 3/4. It's really times 3 on top, but then divided on 4, which is the same as multiplying it by 3/4. So I broke that out. Here's my a, 3/4. Now I'm going to divide my a by n plus 1, but I don't want to write a complex fraction. So dividing by n plus 1 is the same as multiplying by the reciprocal of n plus 1. So that's 1 over 2 plus 1. So I've just broken that out as much as I can just so you can see all the steps. And of course, here's my x, and then I have my n plus 1, which is 2 plus 1, as my exponent. Okay, so this reduces down quite a bit. I just finished that out. Now this is 1/3, and I can cancel my 3, so I just have a 4 on the bottom of my x to the third. So there's my antiderivative. Pretty cool. A little bit more complex, but this is all basic algebra skills that you should have. So now, there's something missing here that we need to account for. Now, what I want you to do is think about that. We haven't discussed this at all, but I'm going to say, what happens when we take the derivative of this expression, 2x squared plus 7? What happens? We use our power rule, so this becomes 4x. Beautiful. This is 7x to the 0. So we take our 0 down, multiply it by 7. This term goes away, okay? So the 7, the constant out here, is gone. That's our derivative. So the question I have for you is, how do we know there wasn't a constant in the original expression? We don't. So what we have to do is we have to do plus c. And this is just a recognition that if this is the derivative, the original function could have had any number out there. As long as there was no variable, it could have any number. So this is actually the antiderivative of an infinity of possible original functions. We can't tell because that part goes away when you take the derivative. So we acknowledge that by putting a c out here. And so that means that this antiderivative is called indefinite. It's not definite. We just know that there could have been a constant. It might not, but there could have been one. So you'll need to remember this when you take your antiderivatives. Always just throw a plus c out there because it could be there, and you've got to let us know that you understand that. It's tricky. Every time I grade tests and quizzes, people miss that. It's not a lot of points, but you might as well get all the points you can get, right? 2 last problems, and I'll let you go. So check this out. Now I've got some expressions that don't immediately fit the structure that we need to apply our antiderivative rule. So the step here is just using some algebra skills that you got from a prior class and transforming these expressions into expressions that fit this form of a coefficient times x to a power. So we've done this year with lots of different expressions, lots of different problems, lots of different topics. So I'm going to ask you, pause the video, do that step to convert, and then take your antiderivative of these expressions. Do both those and come right back. Okay, let's see how you did. So this first one's pretty straightforward. To get it into the correct form, we just have to move the exponent up, which puts it as a negative exponent. Then I can just apply my antiderivative rule and do minus 3 plus 1. There's my exponent, minus 3 plus 1. So it's 1 over minus 3 plus 1 times x to the minus 3 plus 1, which ends up being 1 over minus 2. I got my minus floating out there, but it's the same thing, to x to the minus 2. This is a good answer. Here is a more clean answer. I prefer that. On a test, I'm going to give you full points for that one, but it's really just negative 1 over 2x squared. I think that's a little further simplified, but this is a good answer also. Now let's take a look at the second one. A little more complicated. Kudos to you if you figured out how to go from this complex root expression to an exponent, because that's the key part of that. So the fifth root of x to the third is the same as x to the 3/5 power. So now we're in the correct form to apply our antiderivative rule. Now we've got some fractions, so a little bit of fraction skills are important here, because my antiderivative is going to be 1 over 3/5 plus 1, that's my new coefficient, times x to the 3/5 plus 1. So I urge you, while you're getting the hang of this, just write this plug-in step as is, and then start crunching and combining and doing the rest of it. So 3/5 plus 1 is 8/5. So this becomes 1 over 8/5 times x to the 8/5 power. Now that's good. We're going to leave that alone, but we want to simplify this. Having a compound fraction is a no-no. So we just flip and multiply the bottom one. So that ends up giving us 5/8 times x to the 8/5. Now, sometimes we like to say no fractional exponents. And so in some cases, that's considered more simplified. So I just went back to my root form. And so now I have 5 times the 5th root of x to the 8th power over 8. That's my antiderivative of this expression. Now that you've watched the video, take a moment to jot down some notes, some questions, or a quick summary of the content. You can also re-watch the portions of the video that were a little bit challenging. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.